Okay, good evening everyone, hello. I'd like to wish you all a very warm welcome to the planetarium here at Glasgow Science Centre to the very first David Elder lecture of this year's series, which as always are very, very kindly supported by the University of Strathclyde. We are going to get started in just a second, but as always there's a tiny bit of housekeeping that we need to do before we do. So first off, during the lecture we are going to bring the lights down. It is best if you stay in your seats. If you need anything during the lecture or you want to leave, don't be shy, give me or my colleague Erin up at the back, we wave, we shout, we yoo-hoo. My name is Nina as well, I should probably have introduced myself. We will happily come and get you, and if you do want to leave, we'll lead you out one of the doors at the back. During the lecture we would ask that things like phones, cameras, tablets get tucked away in a bag or in a pocket, and if you can make sure those are on silent before you do, that would be absolutely smashing. Sorry, you okay there? If we can turn it up at the back just a smidge, just to make sure everyone can hear me. It is actually important that everyone can hear me because we're also being joined by an audience on YouTube as well, so it's not just folk in-house, there is also a large group of people joining us online. So the nice thing about this is that everyone gets to be involved, so at the end we are more than keen to get you guys to ask questions, but we will also be inviting questions from the audience on YouTube too. So if you do have a question on YouTube, if you can just preface that with question in capital letters, it'll make it much easier for us to find. What the people on YouTube don't have to worry about is if there's something exciting like a fire alarm. If that should happen, all the lights will come on, our microphones will switch off, myself and Erin will meet you at the back wearing some very stylish high-vis waistcoats. We'll lead you down some stairs and out into that pretty reasonable Glaswegian evening. That is everything I have to say. We're absolutely delighted that we're going to be joined tonight by Dr. Hannah Wakeford, who's joined us all the way from Bristol. We're going to be diving through some exoplanet atmospheres, and given that it's really her that you've come to see tonight, I'm going to stop talking and hand over. So thank you so much for joining us tonight, Hannah.
Yep, there we go. Came right on there. I think you can all hear me, I certainly can. Thank you so much to Nina for inviting me here to give this lecture, and I'm so excited to be in Glasgow. I absolutely love the city. I came to this centre when I was a kid and played around and ran around all over the place, touching everything I possibly could, and I've been lucky enough to visit the city on other occasions as well. It's absolutely beautiful. I'm going to take you on a little bit of a journey this evening. We're going to learn about exoplanets, and in particular, how we look at their atmospheres and what we've learnt from those deep dives. So first off, what is an exoplanet? An exoplanet is a planet that orbits a star other than the sun. So like the planets in our solar system, like the one we're currently sitting on, orbiting around our star, nearly all of the stars that you see in the night sky have their own planets orbiting around them. That means that there are more planets than stars in our galaxy. And there are more stars than there are grains of sand on the Earth. That's a huge number of worlds to discover and explore. And we've confirmed the presence of about 5,000 of these worlds so far. So 5,000 of them across the whole sky. What you're seeing here is a map of the Milky Way. That bright curve of milky dust cutting through, that's our galaxy as we see it from the Earth. Every single dot on this is a planet that has been confirmed, a planet that actually exists, orbiting around another star. That small chunk that I'm highlighting over in the corner there, that is the discoveries made by the Kepler Space Telescope. This is a telescope that was launched in 2009 to specifically look for exoplanets, specifically designed to sit and stare at that small portion of the sky for 3 years to try and measure the presence of alien worlds around other stars. And as you can see, it found thousands of them. It is in fact responsible for over half of the exoplanets that have been discovered so far. And what you can see in the structure there, in the zoom in, is actually the shape of the cameras on the telescope itself. So the imprint of the telescope's cameras can be seen in its discoveries. But those are just our very closest neighbors. If we look at the discovery of planets over time, and I'll play this in a second, you can see that we're looking incredibly close to our sun. So we can watch this tick up. We're going through time here. We're in 2000 now. If you look at the cutout, you can see these dots appearing and appearing. Down here, you can see our position in the Milky Way. Every dot representing a new planet that is being discovered through time. You can see the yellow beam that's shooting out towards the Perseus arm. That's the Kepler field of view. That's the Kepler telescope pointing out from our portion of the galaxy, trying to find these worlds. That big green column shooting towards the center of our galaxy is using a method called microlensing, where we literally use the mass of the planetary system itself to see how it warps the light from a more distant star in the center of our galaxy. That warping of the light can tell us about the mass and the distance from its star that that planet is. So we can see that we're actually aware of just the planets right next to us. And we can take that number and we can expand it to the rest of the stars in our galaxy and get a good idea of how many planets are out there. Now, the observations of these planets have actually revealed that a majority of the worlds that have been discovered do not exist in our own solar system. What you're seeing here along the bottom is the size of the planet, the radius of the planet. Along the side is quite simply the number of those worlds with that radius. I've put on here our solar system planets, from Earth through to our ice giants, Uranus and Neptune, which are about 4 times the radius of the Earth, to our gas giants, Saturn and Jupiter, at 8.5 and 11 times the radius of the Earth. You can see simply from the numbers here that the majority of worlds that have been discovered lie in between the size of the Earth, the largest rocky world in our solar system, to the sizes of the ice giants, Uranus and Neptune. Now, astronomers are notoriously awful at naming things. We are a say what you see kind of people. This first bump close to the Earth are called super-Earths. They're larger than the Earth. They're super-Earths. This other bump, this much larger one closer to Neptune, those are mini-Neptunes. Again, it's a say what you see kind of world. And in reality, because we do not have one of these kinds of worlds in our own solar system, we know next to nothing about them. And this remains a big open question in exoplanet science today that we're hoping to investigate over the next couple of years. But let's put this into context. I want you to go away from this remembering, looking around you, about our planets in the solar system and exoplanets. So what I'm going to do is I'm going to create ourselves a nice little fruit basket. And that fruit basket needs an oddity. It needs a pea. Because the Earth is, in the scale that we're going to use, about the size of a pea. On this scale, our ice giants are about a plum. And our gas giants are a nice round orange. On this scale, we're really looking at the blueberries of the super-Earths and the grapes of the mini-Neptunes. So I hope when you go to the supermarket next, you think about our fruit basket of planets and the oddity that is the Earth, the pea amongst the fruit. So we can look at this distribution of sizes, but this doesn't really tell you enough about these planets. The size of a planet, the radius, is not enough to learn about what that world might be like. Another way that we can look at this is we can look at the size of our planet versus the distance it is from its star. Now, over on this side is closer to the star, over here is much further away from the star. You can already see these planets are much closer to their stars than the solar system planets are to the sun. Now, a majority of this is actually observational bias. It's easier for us to detect planets that are closer to their stars. It's easier because their orbital periods, their years, are shorter, so we can make repeated measurements on a reasonable timescale. For the Earth, we'd need to watch it every single year, years upon years, to build up a signal that we believed. We like repeating things as scientists, and it's the same with our observations. We need repeated measurements to believe them. So the closer they are, the more repeated measurements we can make. But you can also see some clusters in here. This lower cluster of blues, that represents our super-Earths and our mini-Neptunes. This cluster at the top here with that pink dot right in the middle of it, that's what we call our hot Jupiters. They are Jupiter-sized worlds that are close to their star, therefore they are hot. These are the worlds that I really study and try to understand what it means to be a hot Jupiter. So because their orbits are so short, they're so close to their star, they're actually tidally locked. And this means that they have a permanent day side and a permanent night side. One side of the planet is always facing the star. One side is always facing deep space. And this is because the time it takes them to orbit around their star is equal to the time it takes them to rotate about their axis. We can actually see that right here in our solar system. We can see that from the Earth. If we look at the moon, we will only ever see one face of the moon. That's because the moon is tidally locked to the Earth. Its rotation is equal to its orbit, so we only ever see one side of the moon. Instead of these planets orbiting around another planet, they're orbiting around a bright, glowing ball of plasma, which means they are heated dramatically on one side, whilst the other never ever sees that daylight. And they orbit different kinds of stars. And when we say they orbit different kinds of stars, we don't mean they're just slightly different. We mean that they can orbit stars that are as small as just a tenth the size of the sun. That's the equivalent size of Jupiter, but a star that's glowing. All the way up to giant, big blue stars, which are over 10,000 degrees. So these hot Jupiters and these planets that have been discovered come in a huge variety. So we have a lot of things to explore and try and understand. And the type of star they orbit and that distance that we looked at before can really tell you a fundamental thing about what the temperature of the planet might be. So we're looking at here where we go distance from that star again. This time we're looking at the mass of the star itself rather than the mass of the planet. And what you can see is this big blue line that goes through it there. That's the temperature range of liquid water existing. So that's everything from 0 degrees to 100 degrees. And you can see for the small red stars, you have to be much closer to the star for the temperatures to be within that range. Whereas as we go up towards the sun, which is hotter, larger and hotter than those small red stars, you have to be much further away. So the distance from your star and the size of your star really, really matter to define what kind of temperatures you have. But a planet's atmosphere plays a huge role in the energy budget of that planet. how it takes in that energy from the star, absorbs it, and re-releases it back into space. We know from the Earth that if we just took the distance that we have from our star, we should be about 20 degrees below zero. But on average, we're about 15 degrees above zero. And that's all to do with our atmosphere. So when we're looking at these planets, we can make estimations based on their mass, their radius, their distance from their star, their type of star. But without really knowing about their atmosphere, we can only make guesses as to what they're like. And clouds play a huge role in the energy budget of our atmosphere. This is looking at the Earth in reflected light on this side over here, and in emitted radiation, so emitted light. So we're looking in the ultraviolet over here at light that is literally being bounced off our atmosphere, or off the surface, or off the oceans. And this one is in infrared light, in heat. And you can see that there is a very strong link between the clouds and the radiation that we see from this planet. So we need to understand not just what the atmosphere might be made of, but what other things might be there as well. And then there's this nice fourth dimension we have to deal with: time. We know from the Earth that it has actually looked vastly different over the course of its evolution. We can see right at the top here, this is our Archean Earth. This is our hell Earth. The atmosphere was mostly methane and carbon dioxide. It was a pale orange, hazy dot. Over time, that changed until we get to today's atmosphere on modern Earth, where we have an ozone layer composed of O3 molecules that are continuously destroyed and built. We have mostly nitrogen atmosphere, which all came from the rocks that make up our planet, outgassed in its early lifetime. And we have water in our atmosphere as both a vapor, as a gas, and as liquids and solids in our clouds. So we have to think about time components for these atmospheres as well to really understand the nature of these planets we're looking at. And even today, we sit within that nice little temperate zone of our star with our atmosphere shielding us, but there are some barely habitable parts of our planet. And this is due to the circulation patterns of our atmosphere. This is actually a picture that I took in Death Valley in the United States, where it recommends not walking after 10 a.m., but it doesn't tell you when you're allowed to come back again. Always baffled us. But the circulation of an atmosphere is a really key factor for understanding where in the planet, what kind of weather you might get. So how can we measure the atmosphere of distant exoplanets? What are they made of, and what is that atmosphere like? So the main way we do this is by looking at planets that transit their star. So with the transit method, we're literally looking at the star. We're not looking at the planet itself, but we're inferring its presence from the way that it blocks out the light. So what you're seeing here is a planet passing in front of its star from our point of view, and it blocks out some of that star's light. And the amount of light that it blocks out is a ratio of the areas of the star and the planet. So if we know the size of the star, which we can estimate from its temperature, its brightness, then we can work out the size of our planet. Now, using this transit method allows us to access only about 10% of all potential planets in our galaxy. And that's because it is so dependent on the orientation of that planet, such that it does in fact pass in front of its star from our point of view on the Earth. But with this small fraction of worlds, we've discovered thousands of planets that we can look at in this way. And that size of the planet will actually change depending on what wavelength, what color you look at it in. So this is a picture of the Earth's atmosphere and the moon in the background there. This is a real color image of our planet. If we look at a specific wavelength, then we can actually see that it changes in size. If we look again at a different wavelength, again the planet appears to physically change in size. We can go backwards and forwards between these two. You can see here that the moon is not changing in size. And that's because the moon does not have an atmosphere. What we're looking at here is the presence of ozone in the Earth's atmosphere, physically blocking out more light because it's absorbing it. We can do this with the transit method as well, because some of that star's light is shining through the planet's atmosphere before it reaches us. And that light is being absorbed in that same way by different things in that planet's atmosphere. And the wonderful thing about physics and chemistry and our natural world is that each atom and molecule has its own unique fingerprint. So we can look for those in the signatures of these atmospheres. So it actually appears, when we're measuring this, like the planet is physically changing size with color. And that's the imprint of that planet's atmosphere on the light that we're measuring. So from this, we can work out what the atmosphere of these different planets is made of. The bigger the atmosphere, the easier it is for us to measure their spectra. This is showing you the difference between a hot Jupiter, a warm Neptune-sized world, and a temperate, rocky Earth-sized world. The Jupiter-sized planet literally has more atmosphere. Therefore, we're collecting more light passing through it, so it's easier for us to make those measurements. But we've been able to measure atmospheres from these giant Jupiter-sized worlds all the way down to things the size of the Earth. And this is just showing you a handful of the measurements that have been made by the Hubble Space Telescope over the last 10 years. I've been lucky enough to work on every single one of these. And from this information, we've been able to detect the presence of water vapor in its gas phase in 80% of the exoplanets that we've observed with Hubble. Now, when I say water vapor and I mean the vapor phase, these planets are often incredibly close to their star. Therefore, the temperatures on their day sides are very high. For many of these worlds, they're over 1,000 degrees. That's hotter than sitting underneath a rocket as it's taking off. So these atmospheres do not have liquid water in them. But JWST, newly launched telescope, launched on Christmas Day last year, started taking science observations in July. This is going to give us access to 10 times the number of planets and their spectra that I just showed you. And I'm highlighting here just 2 images from the very first releases from JWST, which I absolutely love, because this is an image of a star with JWST. Those spikes that you're seeing, those are called the diffraction spikes. And they actually map to the telescope itself. This is a selfie taken by a telescope 1 million miles away from the Earth. It's definitely a modern telescope. But the telescope itself is composed of 18 gold-plated segments that you can see here with their characteristic hexagon shape. These dark lines and that middle bit are the arms that are holding the secondary mirror. It's a reflective telescope, so it captures the light, that reflects back onto that secondary mirror. It's a beehive taking a selfie is really what's happening here. And that beautiful gold-plated mirror and those arms that you can see are what causes these very characteristic shapes in the spikes. And that's all just fundamental physics there. So I love just seeing that and going, every time I see an image with spikes in that way, I know it's from JWST. But the really exciting thing for me and for hundreds of my exoplanet friends, and hopefully for you guys as well, is that we've been able to use this massive 6.5 meter telescope, 6.25 times the area of the Hubble Space Telescope, to measure the atmospheres of exoplanets in ways we have never done before. This behind me is one of those measurements that we've made. This is an artist's impression of a planet that we have been observing called WASP 39b. The WASP is for the survey that discovered it. The 39 is that it's the 39th star that they have a planet discovered around. And the B is the planet itself. And what you're seeing on top here is the spectrum that we measured with JWST. But I'm going to highlight over here, this is what we previously had measured for this planet. So hopefully you can appreciate how much better that is compared to what we previously knew. A better way to appreciate that is by literally looking at it unfold in front of your eyes. These previous measurements, we were able to predict that the atmosphere contained CO2, carbon dioxide. We made that prediction based on 2 data points. Ridiculous, I know. We're working on it. But what JWST was able to do in a single observation was showcase that, in fact, we are measuring carbon dioxide in this atmosphere. And we were pretty good with our predictions before. But the amazing thing is that we've learned so much more about this planet's atmosphere by being able to resolve that feature. The height of it, the width of it, the way that it changes with wavelength. This gives us clues as to how that planet itself formed. And I'm showcasing these. We literally published them just 2 weeks ago. So this is brand new science that has not been shown before. And in just the first 2 months of science that JWST has been doing, since July, we have had a whole universe of things revealed to us. I'm just going to take a moment to look at this. This is a composite of images that have been released in just the last 2 months from JWST that I have put together for you in the shape of its characteristic mirror. We can go from the top up here with Jupiter in our own solar system. These bright green portions of the atmosphere are real observations of aurora in the atmosphere of our gentle giant. Down here is a brand new image which was released yesterday evening of Neptune. And what you can see really clearly are the beautiful rings around Neptune itself, with some of the moons that you can also see in here. One thing that isn't commonly known is that every single giant planet in our solar system has rings. Saturn has the most spectacular of ring systems, yes, but Jupiter has rings, Neptune has rings, and Uranus has rings. Those giant planets have these dynamic environments all around them that we're trying to understand more. You can see things like the Orion Nebula down here. Galaxies in clusters where they're tidally ripping each other apart. Beautiful nebulae which represent the death of a star. And some of the most distant parts of our universe with these warped shaped galaxies which are being lensed by this cluster so that we can see back around 13 billion years. One of the first spectra that were released from JWST was in fact that of an exoplanet. This exoplanet was called WASP 96b. And with this spectrum, they not only showcased the beautiful images that you can do with JWST, but the amazing science that you can get of distant worlds. This observation here confirmed the presence of water vapor in this planet's atmosphere, like what we measured with the Hubble Space Telescope, but a hell of a lot better, let's be honest. We were also able to measure multiple absorption features from water because we've got extended coverage in the wavelength space. But another thing that was really interesting for this world is revealing the influence of clouds in its atmosphere. I said before that clouds play a really big role in the energy of a planet's atmosphere. So let's look a little bit more about what these clouds might mean. So if we look at the spectrum of a planet's atmosphere, this is what we expect to measure. But if we add clouds to this spectrum, we can actually see that what we would measure would change. So we can add two different kinds of clouds here. One is highly scattering. This represents clouds made of small particles in the atmosphere. And one is kind of cutting everything off. This represents large particles in that planet's atmosphere. But the clouds in these exoplanet atmospheres are fascinating for another reason. What you're seeing here is the temperature along the bottom here and the pressure along the side here. As we go up, we're going higher in the atmosphere. The pressure is decreasing. As we're going along here, we are going up in temperature. I've put on here the temperature and pressure profiles of our solar system worlds. I've also put on some temperature and pressure profiles of some exoplanets. Remember, these planets are so close to their star, they're incredibly hot. So their profiles look very different. But that has a major consequence on the clouds in these atmospheres. For our solar system, we have clouds made of methane, ammonia, water. For these planets, because they're so hot, their clouds can't be made of these substances. They're vaporized in the atmospheres of these worlds. Instead, the clouds that are forming in these planetary atmospheres are made of things like disodium sulfide. They're made of magnesium silicates, literally the rocks that we're standing on, the sand on our beaches. They're made of molten iron. And they're made of corundum, the basis for rubies and sapphires. The clouds in these planetary atmospheres are the gems and jewels of our planet, floating up there, obscuring the light, in their own special ways. And clouds and dust of these kinds of materials exist in lots of different places, not just in these planetary atmospheres that are so hot and tidally locked to their stars. They exist in the planetary nebula from a dead star. They exist in the nebulae that then go on to birth new stars. They also exist in the atmospheres of brown dwarfs, which are objects that aren't quite big enough to be a star and fuse at their core, but they're way too big to be a planet. And we know that there's a relationship between the temperature and the type of clouds that you're going to form. And that relationship can be seen through the atmosphere of a planet, because as you get deeper into the atmosphere of a planet, the temperature increases. And these planets have atmospheres that are incredibly deep, thousands and thousands of kilometers. So as you go deeper through the atmosphere, you're changing what kind of clouds you might expect to form. And at these very high temperatures, we're expecting clouds made of these liquid metal iron and these magnesium silicates high up in the atmosphere. And that's what we're measuring, obscuring the light in these spectra from JWST. This is the first time those kinds of clouds have actually been measured, and we're able to say definitively that planetary atmospheres have clouds made of liquid glass. There we go. But the really exciting thing is that just like atoms and molecules, these clouds don't just block out the light in different ways. They don't just obscure the measurements of water or carbon dioxide. They actually have their own features. They interact with the light in their own way, which we can see and measure as absorption in the atmosphere. And these are through what is called a vibrational mode. Now, a vibrational mode is literally how the atoms and molecules move relative to each other. And there are lots of different ways of doing this. It's a nice workout if everybody wants to stick their arms up, try not to punch anybody in the face. We've got our pumping modes. We've got our waving modes. And we've got our spanning modes. All of these motions manifest themselves through different energies, and those different energies come out as different wavelengths. So we can see how these different materials are blocking and absorbing that light through the different wavelengths that they're absorbing, creating this motion. And the key thing is that these absorption features are right in the wheelhouse of JWST. So with the Hubble Space Telescope, we've been observing the UV, the optical. We can look at the scattering profile of these clouds. We can say, oh, it must be made of small particles, but we don't know what it is. But with JWST, we've been able to see and show that actually that cloud is a magnesium silicate. It is a corundum, rubies and sapphires in that planet's atmosphere. And these observations are just going to grow. We don't want to look at one planet. We're not stamp collecting. We need to look at a whole diverse range of planets to really understand what the relationships are between the star, the temperature, the distance, the size, and how that manifests in what the nature of these worlds and atmospheres is like. So let's journey to some of these worlds and have a look at their atmospheres and see what it would be like. We're going to take our TARDIS, and we're going to journey to the atmosphere of a distant planet. What we're seeing here is quite literally the star this planet orbits. through the planet's atmosphere. It's not quite like the sunsets that we see here on Earth. What's the main difference? Nothing? It's blue-green. It's pretty different. This blue-green is caused by the presence of sodium in the planet's atmosphere, absorbing the orange light. If you take out the orange light, you end up with this beautiful blue-green sunset. It's pretty nice. So let's journey to another world and see what might be out there. This is one of my favorites. This is our film noir world. You've got this beautiful grayscale from our deep dark all the way up to bright white. This comes from one of the most boring of measurements that you can make. It's a flat line. That is just a straight line of data points. Nothing in there. And you'd think, oh, we expected to measure the bumps and wiggles of water and sodium and who knows what in this atmosphere. No, we get a flat line. And most astronomers, I'll admit, were quite disappointed. I got very excited. Because the temperature of this planet is over 2,300 degrees on its day side. That's so hot that not a single thing should exist as a liquid or a solid. Not a single thing. But this flat line suggests that there is something in the atmosphere that is blocking the light in such a way, scattering that light, that it has to be a liquid or a solid. There has to be clouds in this planet's atmosphere. That means that there is a big temperature difference from its day side, where it's over 2,000 degrees, to its night side, so that we are literally condensing material into rocks as we go from our day side of the planet across the terminator to the night side. So we can learn about the temperature structure and the dynamics of the atmosphere from this flat line. It means that the heat from the star is not making it around the planet. But more importantly, because of its temperature, the only clouds that can exist in this planet's atmosphere are our corundums. Those are our sapphires and our rubies. So this planet's atmosphere has clouds that are made of corundum and aluminium oxide. When you contaminate it with different elements that we know to exist from the stars' measurements, from understanding how these planets form, you end up with gems and jewels of all colors. Those gems and jewels of all colors forming those clouds, liquid and solid droplets suspended in this atmosphere, create this beautiful film noir gray landscape. Off to a world which is a little bit more familiar. This is more like the kinds of sunsets that we might experience here on the Earth. A beautiful deep red going up through the oranges, yellows, white. We see this as our sun sets, but we see each of these colors in turn as our sunsets. This planet is so big and so close to its star, you would see all the colors of sunset all at once in this beautiful scale here. This is because the atmosphere is scattering the light at the blue end, just like our atmosphere does. But the reason it's scattering that light is not the same as ours. Our skies are blue because of nitrogen in the atmosphere scattering that blue light more than the red light. That's the same thing that causes our red sunsets. You can see this planet in comparison to the sunset size that we get on the Earth. We're in a vastly different situation here. We're much closer to our star. We're a giant planet. The atmosphere is about 1,000 degrees, much colder than our previous world we were looking at. In the atmosphere of this planet, there are clouds that are made of that liquid glass. That liquid glass scattering the light in the blue, meaning that you get these deep red sunsets. This is an artist's impression of the planet. It would actually look a beautiful deep blue, just like our world does. But unlike our world, because it is so close to its star, it is tidally locked, has a permanent day side, permanent night side, the winds on the planet are being forced around at supersonic speeds. In fact, the winds in this planet's atmosphere have been measured to over 5,000 miles per hour. The fastest winds that have ever been recorded on the Earth are 250 miles per hour in a hurricane. This planet has winds whipping around the atmosphere, carrying shards of molten glass horizontally all the way around the planet. It's a beautiful marble blue. It's got great red sunsets, but this is not a tourist destination. So with our journey delving into these beautiful planetary atmospheres, learning more about how their spectra can really tell us about what they might be like, we really only have more things to learn and discover. We have questions about what does this mean for other planets of the same size? Would they look similar? Our solar system is full of incredibly unique and diverse planetary atmospheres. Every planetary atmosphere in our solar system is different. In fact, you can see on here a moon masquerading amongst the planets. Anyone spot that? Yeah. Titan in the middle here. That's not Saturn. How dare it take Saturn's place? Titan is the largest moon of Saturn. It is also tidally locked to Saturn. One face of Titan faces Saturn and one faces deep space as it orbits. Titan is the only moon in our solar system to have a stable atmosphere. Its atmosphere is made up mostly of methane. It has lakes and seas, and it rains on this world, on a moon. But that rain is made of ethane. It's made of essentially alcohols. It's hydrocarbons. The lakes are incredibly deep, but you'd never get the bends from diving through them because the density of the planet and the gravity is so low. In fact, if you stood on the surface of Titan, which is made up of solid ice, by the way, mountains of solid ice, you could flap your arms and fly. Because the gravity is low, the atmosphere is thick, and hopefully you've got some muscle mass you're taking with you. So our solar system itself just showcases a huge diversity of chemistry, of physics, of dynamics. And we're still only just learning about the diversity of these exoplanets. There are hundreds that we will be investigating in the next couple of years with JWST alone. So I encourage you to keep an eye out in the news. Keep an eye out on Twitter, on whatever social medias, because we're going to be learning so much more about these alien worlds. And through that, we can learn more about our solar system and the place it holds in our local galaxy. So with that journey and the possibility of future, I'm going to leave you with this beautiful hexagons of discovery that are being made right now. The newest one just yesterday, showcasing the beauty of planetary atmospheres. If you like exoplanets and want to know more, please check out Exocast, the Exoplanet podcast that I run with my co-hosts Andrew Rushby and Hugh Osborne. We love talking about exoplanets, even when we're not quite the most expert at the topics we're covering. You can also read more about the journey that it takes to form a planet, what happens to a planet after its star dies, and as the universe goes to its inevitable death. In Bang! 2 exclamation points. This is the updated version to the original Bang. It is a complete history of our universe with about 9 billion years worth of updates in there for you. But thank you for journeying with me, and I really look forward to all of your questions.
Thank you so much, Hannah. You can see why people call it the Just Wonderful Space Telescope.
Oh, yeah.
I think that describes it quite nicely. We do have some time for questions, so if you do have any in the audience, feel free to pop your hand up. And if you do have any on YouTube, I'm here to grab them for you. If you just pop question in capital letters, I'll be able to see it a bit more easily. You're all stunned into silence by those images. There's one up at the back there.
No, that's great. So the question was, what determines whether something's tidally locked so that we've got a rotation rate for the Earth, for example, that doesn't anywhere near match our orbit around the sun? We take 365 days to orbit our sun and we rotate in 1. That's a very different fraction. So what is it that causes that? And it's actually a ratio between the masses of the bodies and the distance they are from each other. So if you've got this really, really big thing like a star, you've then got this planet that needs to be a certain distance for it before it's tidally locked to it. So with our moon and the Earth, the ratio of those sizes is about the same as a hot Jupiter to the stars that we're looking at. And those distances, again, need to be that same ratio. So we see throughout our solar system, most of Jupiter's moons are tidally locked to Jupiter. So all the Galilean moons are tidally locked because the size ratio of the planet and those moons and the distance they are from it mean that that happens over time. And it's all to do with a fundamental law of physics, the conservation of angular momentum. So you need to conserve a lot of different properties. As you go closer to your orbiting body, you need to get rid of some of that energy somehow. And you do that by essentially they're pulling on each other. So they're just pulling on each other, and as you pull on each other, the tides that are the forces have to balance out. And over time, when those forces balance out, you become in sync with each other. So there are some systems that we might be seeing that are young and not tidally locked yet, because there's a time scale associated with that. That force, that pulling on each other, takes time. And we can calculate roughly how long that time is, depending on the sizes of the bodies and the distances they are from each other. But most of the worlds that we're looking at are actually really old. They are fully evolved systems like our own solar system. They've been around for billions of years, so we know that they've settled into this kind of equilibrium state. So these close-in planets, because of their ratios of distances and their sizes, we know that they must be tidally locked. I hope that answers the question.
YouTube's being quite quiet, so do feel free to take questions from the audience.
So it's a much slower process than kind of, it doesn't really overshoot. So the question was, is there an overshoot in the tidal locking kind of process? Does it go a little bit too far and then come back to that settling? It takes such a long time to do this, so we're talking millions of years, that it wouldn't necessarily overshoot, it would just settle into that equilibrium. So the question was, can we tell if the atmosphere has changed in the time it takes for the light to have reached Earth? No is the quick answer, but I'm going to take liberties and explain why. So a lot of these planets that we're looking at are somewhere between 40 and 1,000 light years away. So we're looking at planets that are 40 years older than the present, or thousands of years ago. Light is a beautiful time machine like that. But the light that we receive from them when we're looking at these events, they're happening on the order of hours. So the transit itself, the measurement we're making, is only a couple of hours long. So that's essentially no time at all for these planets. There is a chance that we can measure weather phenomena, so local changes in the atmosphere for these planets, if we went back and observed that planet again and again and again. However, then you have to beg for observing time from these wonderful telescopes, and it's quite expensive and precious. So we're hoping to be able to do that, but we haven't got a definitive measurement of time processes in these planetary atmospheres. We do, however, have those weather patterns measured for brown dwarfs. So brown dwarfs are often free-floating. They form, we think, like stars, but they don't gather enough material. But they have atmospheres very similar to planets. So we can use them as this kind of middle proxy for trying to understand these kind of phenomena. And they often rotate on the order of 2 hours. So they're very fast rotators. So we've actually been able to measure some of these brown dwarfs over the course of their rotation, and we see changes in the light from them. And those changes in the light tell us that there are different parts of the atmosphere that are emitting light in different ways. And a lot of that has told us about patchy clouds in the atmosphere of these brown dwarfs. So patches of the atmosphere that have clouds, patches that don't have clouds. So we know that weather phenomena are likely to happen. We've been able to measure the wind speeds of some of these planets, like I said. But to get an actual change in the spectrum, that's something that we haven't definitively done yet.
We've got time for one more question, I think.
All right, in the back. So the question was, from these tidally locked planets, they're going to have a hottest point, and then temperature's going to change as you go around. Are we able to measure different cloud types in these planets from their hottest point through to their coolest point? Well, one of the things that we have actually measured for these planets is, in fact, that the hottest point in their atmospheres is not directly underneath the star. So you'd think that the hottest point in the atmosphere is on the equator, directly under that star's light. It's tidally locked, it's always on that one point. That should be heated up continuously by the star, the most. What we've actually found is that the hottest point of the atmosphere is shifted slightly. Still roughly on the equator, but it's shifted eastward. And this is because of the relationship between the heat coming into the planet's atmosphere and the planet re-radiating that heat. And the transport of those winds in the atmosphere mean that the hottest point of the atmosphere is not directly under the star, but shifted, because that heat is being literally transported away so quickly. So we've been able to tell that about the temperature structure of these planets. In terms of the clouds and the materials as a function of temperature, that is something that we are going to be able to measure for the first time with JWST. Now, we're very much in the first couple of months, but spoiler alert on YouTube and everywhere else, there's gonna be differences. Because this hotspot is shifted, so because there's temperature is shifted a little bit, we actually see that one side of the planet is going to be different from the other side of the planet. So we can actually make measurements and try and understand the spatial distribution of things like clouds. We can understand if there's more water on this side than this side. That tells us about the temperature structure of either side of the planet. And we can start to actually generate three-dimensional maps of these planetary atmospheres. Believe it or not, planets are three-dimensional. Everything I've shown you is squishing that into one dimension. That's not right. With JWST, we're actually going to be able to realize these planets in 3 dimensions, understand about their composition, what they're made of, deep into their atmosphere, high up in their atmosphere, and in latitude and longitude. So we're going to be able to generate these 3-dimensional maps and understand even more about the relationship between the chemistry and dynamics. So we've got a lot of things to learn.
That's brilliant. Thank you so much for answering all those questions and for such a fantastic lecture, Hannah. I don't think I'm alone in hoping that you get more time on the JWST to hopefully answer some more questions that the audience might have.
And one final thing, for all of you lovely people who have shown up today, I have bought some JWST stickers for you all, so you'll be able to collect one of those as you leave.
Erin is poised and ready with those stickers to hand them out. So just before you go, I just want to ask you all in joining me in saying a massive thank you to Hannah for kicking off the lecture series in such fine style. Thank you so much. And as you head out tonight, you're just heading out through the same door to the one that you came in. Erin will meet you with your stickers. And yeah, we'll be emailing out a wee survey just to get your feedback because we'd love to hear from you. So thank you so much for coming, folks, and enjoy the rest of your night.
Thank you.